Have you ever stopped to think about this? The entire AI revolution, from chatbots to self-driving cars, is pretty much being built on top of hardware that was originally designed for video games. So how did the tech that gave us amazing graphics become the engine for artificial intelligence? Let's get into it. So here's what we're going to cover. We'll start with the AI computation problem, then meet our two processors, understand how they work differently, trace the GPU's journey from gaming to AI, see why they're such a perfect match, and then look at what all this means for the future. All right, first up, the AI computation problem. You've probably heard that modern AI needs a ridiculous amount of power to run. The big question is, why? And that brings us to the central puzzle, right? Why is a technology that's changing literally everything from medicine to finance so dependent on hardware that got its start rendering worlds in games like Quake and Doom? Well, the answer is all about how they approach problem solving. Okay, so let's meet the two main characters in this story. In section 2, we're talking about two workers, two jobs. And those workers are the central processing unit, the CPU, and the graphics processing unit, the GPU. The easiest way to think about them is like this. The CPU is your specialist. It's a master of handling really complex one-off tasks. The GPU, on the other hand, is a massive army, designed to do a huge number of simple things all at the same time. I love this analogy from a Reddit user named Auclair. It just nails the difference perfectly. They said, the CPU is a handful of college professors, the GPU is a gymnasium full of fifth graders. Think about it. If you need to solve a few really tough calculus problems, you want the professors, right? But if you need to solve a million simple addition problems, well, that gym full of fifth graders is going to get it done way, way faster. So, what's the actual science behind that great analogy? Well, that takes us to section 3. Sequential versus parallel processing.
The CPU, our specialist, it works using sequential processing. That just means it does one thing at a time in a very strict order. And this is perfect for most of the stuff your computer does, where step B can't happen until step A is finished.
And then you have the GPU, our army. It uses parallel processing. It's built to handle thousands of simple instructions all at the exact same moment. This makes it insanely efficient for these huge jobs that you can just chop up into little independent pieces.
This table breaks down the difference really clearly. You can see a CPU has just a few super powerful cores running at a really high speed, like 3 or 4 gigahertz. A GPU, though, it's got thousands of simpler, slower cores running at maybe 1 gigahertz. So here's the bottom line. CPUs are built for complex jobs, one after another. GPUs are built for repetitive jobs all at once.
So how in the world did this piece of hardware for making games look good become the cornerstone of AI? That brings us to section 4, the evolution of the GPU. This timeline kind of shows you the key moments. Back in '94, Sony first uses the term GPU for the original PlayStation. By the early 2000s, some smart researchers were already thinking, hey, maybe we can use these things for more than just graphics. But the real earthquake was in 2007. Nvidia released its CUDA platform. This was basically a key that unlocked all that parallel power for any developer to use for anything they wanted. And by the 2010s, AI researchers were all over. Which leads us right to the heart of it all in section 5, why AI loves parallelism. It just turns out that the GPU is the perfect tool for the job. And the reason why is because training in AI is what computer scientists call an embarrassingly parallel problem. I know it sounds funny, but it's a real term. It just means a task is so easy to split up into millions of tiny, independent pieces that can all be worked on at the same time, without any of them needing to check in with each other. Rendering graphics was the original example of this, right? Figuring out the color for millions of individual pixels on a screen. But it turns out lots of other huge problems work the same way. Things like scientific simulations, crypto mining, and the big one for us, training AI neural networks. And here it is. This is the main takeaway. Training an AI model is the absolute perfect job for a GPU. It's just doing millions and millions of pretty simple math calculations over and over again. And every single one of those calculations can be done on its own. It's the perfect job for that army of cores to just chew through all at once. The CPU's professors would get totally bogged down, but the GPU's gymnasium of fifth graders gets it done in record time. So what does this all add up to? Well, we're now in section 6. The future is parallel. This whole shift is really kicking off a brand new era of computing. And this isn't some recent breakthrough. AI pioneer Geoff Hinton saw this coming a long time ago.
He said that back in 2009, he told a room of 1,000 researchers that they should all go out and buy GPUs because they were going to be the future of machine learning. And wow, was he right. The ability to process all that data in parallel wasn't just a small step up, it was the key that unlocks this whole AI revolution we're seeing today. And that leaves us with a really interesting final thought. When you think about the world's biggest challenges, from climate modeling to discovering new drugs, so many of them are becoming these massive data-heavy problems. Seeing how much success GPUs have had with AI makes you wonder, as our problems get bigger, will all computing eventually have to become parallel? What do you think?